Now that we've talked about imaginary numbers, we can now start including imaginary numbers as part of our solution set or set of zeros for a polynomial function, which is a good time to talk about what's called the fundamental theorem of algebra. Now, I don't know about you, but that sounds pretty important to me, the fundamental theorem of algebra. Now, fortunately for us, just because something is important in math doesn't always mean that it's complicated, and this is a good example of that. The fundamental theorem of algebra simply states the following, that let me just go ahead and I already wrote it out previously, so I'll just include this here. It says that every nth degree polynomial function has exactly n complex zeros. That is to say, if, for example, if you have a fourth degree polynomial function, you're going to know that you have exactly 4 complex zeros. By that word complex, we include both real and imaginary zeros. That's it. Now, as a follow-up to that, there's the linear factorization theorem, which essentially states the same thing, but whatever your degree is tells you exactly how many linear factors that you have. So in which case, if you have a fourth degree polynomial again, then that means you're going to have 4 linear factors where your zeros are complex numbers. They could be both real numbers or imaginary numbers. Now, for the intent of this particular course, an important distinction that I want to make is the following, that all of our coefficients for our polynomial functions are going to be real and rational coefficients. Real and rational coefficients. And what that means for us is the following. If we are going to be working with polynomial functions that contain specifically real and rational coefficients, that means all of our imaginary and irrational zeros come in conjugate pairs. So that is to say the following. So for example, if you have I as one of your zeros, that means you know that negative I must also be a zero. If we know that, for example, 1 plus root 3 is a 0, this is an irrational number, that means 1 minus root 3 must also be a 0. So we're going to leverage that information, the idea that all of our zeros have to come in conjugate pairs in order to ensure that all of our coefficients are both real and rational. And that's going to come in handy when we start working through a few of these problems. So let's try a couple of these right now. Let's start with this first example here, where we're being asked to find all the zeros of this polynomial function. And the first thing I always ask myself is, can I factor this polynomial? And at first glance, you might think that you might be able to factor this one by grouping, but if I factor out this x squared from these first two terms, I'm left with an x minus 3. So factoring by grouping isn't an option for us here, so we can't do that. So what we can do is look at the possible rational zeros of this function. So we're going to look at p over q, which are the factors of my constant, plus or minus 1, over all the factors of my leading coefficient, which is just plus or minus 1. So if I divide here, I just have plus or minus 1. So that's nice for us. The rational roots theorem tells us that for this function here, where I'm going to start setting this up synthetically, for this function here, if there is a rational zero, if a rational zero does exist, it's going to be from this list of p over q. So I can try positive 1 just to start off. So I'm going to do the synthetic division. I'm going to bring down that 1, make this 1 here, make this negative 2. Negative 2 times 1 is negative 2. And we're going to add these columns. And there you have it. We see that 0 is our remainder, which tells us that x minus 1 is indeed a factor. So far we can say that one of my zeros is x is equal to 1. And so far one of my factors is x minus 1. We know that this is one of our factors. So look at our resulting coefficient, quotient, which represents all the coefficients of our polynomial function. So from here, I can say x squared minus 2x minus 1. Now you can continue to try the synthetic division here, but when we get a quadratic, it's often nice just to look at that and ask ourselves, can I factor this, or try to find the zeros for this using either the quadratic formula or completing the square. I see that this is not factorable, so I'm going to try to use a quadratic formula. So negative b, which is just positive 2, plus or minus b squared, 4 minus 4ac, all of this over 2a. And if I break this down a little bit further, I can say this is 2 plus or minus 4 plus 4, which is 8. So I see my radicand is 8. So I'm going to simplify, well, let me just write that first. All of this over 2. So this is 2 plus or minus, if I simplify my radical, I got 2 root 2 over 2, which is just 1 plus or minus root 2. So I've got two zeros from this. I have 1 plus radical 2, 1 minus radical 2. So I'm now going to include these as my zeros. And then that means, let me keep writing this in purple, that means my other factors are x minus 1 plus root 2, x minus my other 0, 1 minus root 2. So I didn't have to list all my factors, but I went ahead and I'm listed it there so you can compare them to the zeros. And here are the zeros that I found. So I've got a total of 3 zeros, which match up with the fact that my degree was equal to 3. So I've finished finding all the zeros here. Okay, let's try another problem now. Let's try a problem such as this here. Pause the video right now and ask yourself, can I factor this? And if so, see if you can factor it. Well, if you look at it carefully, you actually can factor this. And we're going to factor by grouping. That is to say, we're going to factor it as such, the first two terms, the next two terms, and then the final three terms. So let's break each of these down. So f of x, I've got here, let me just actually make that a little bit so I can see better. From here, I see my common factor is x to the fourth, and x plus 3 is left over. The next two terms, I've got x squared. Actually, negative 7x squared is something I can factor out. So that's x plus 3 left over here. And then from my last binomial, I can factor out a negative 18, and x plus 3 is left over there. And I see that I have a common factor of x plus 3 in all of these groups. So I can factor out this x plus 3. And what we're left over with is x to the fourth minus 7x squared minus 18. So from this, I can already tell that one of my zeros is going to be negative 3, but we'll take care of that in just a moment. Continuing on here, ask yourself, now with this resulting polynomial here, can we factor that? If we can't, then we should try synthetic division. But if we can actually factor it, then that'll make our lives a lot easier because we won't have to guess and check. And I see here that if I actually factor this like it's a quadratic, I can. So I got here 9 and 2. This is going to be negative 9. This is going to be positive 2. And from here, now I can set my function equal to 0 and start solving. From here, I can say x is equal to negative 3. From this factor here, I can set x squared equal to 9, and I should get x is equal to plus or minus 3. From here, I can set, let me just write this to the side so we can all see that, x squared plus 2 is equal to 0, so x squared is equal to negative 2. If I extract the roots of both sides, x is equal to plus or minus root 2 I, or I root 2. So from here, plus or minus x is equal, let me write that again. X is equal to plus or minus I root 2. And I'll notice that I have a negative 3 mentioned here twice, so I'm going to actually write my final answer with all the multiplicity being indicated. Multiplicity of 2, positive 3, and plus or minus I root 2. So these are all my zeros. I've got 5 zeros here. My leading degree here in my original polynomial function was 5. I noticed that 3 of my zeros are real and 2 of my zeros are imaginary. Okay. All right. Now let's try another problem where this time I want to find a fourth degree polynomial function with real coefficients given these zeros. Okay. So I noticed that 2 of my zeros are negative 1. So I can say f of x is equal to x minus negative 1 or x plus 1. And since I have 2 instances of that, I can just square that. I also see that I have 3i as a 0. And I mentioned earlier that if I want to make sure that I have real coefficients, that anytime I have a imaginary 0, its conjugate must also be a 0. That is to say, negative 3i must also be a 0. So I'm going to state my factor as x minus whatever my 0 is, so 3i. And then if negative 3i is a 0, x minus negative 3i or x plus 3i has to be my other 0. Now, The problem didn't state it, but know that in my course, I'm going to want you to write these polynomial functions in general form, and it's a good idea just to know how to do that. So I'm going to need to expand all this out. Fortunately, it isn't too bad. X plus 1 squared is x squared plus 2x plus 1. X minus 3i times x plus 3i. The nice thing about multiplying conjugates out is that you can really just apply the difference of squares. It's just a squared minus b squared. So x squared minus, so now I'm going to subtract. Now what is my b? My b is 3i, so this is going to be 9i squared. Now, just to clean this up a little bit, we know that I squared is equal to negative 1. I squared is equal to negative 1. So that means this is x squared minus negative 9, or x squared plus 9. So now let's just go ahead and distribute this out. This is going to be x to the 4th plus 2x cubed plus x squared. Now I'm going to multiply this 9 times each of those terms, so plus 9x squared plus 18x plus 9. If I add all this up, and there is my function in general form. I've got a 4th degree. I had 4 zeros. 2 of them were real, 2 of them were imaginary. And I can see my linear factorization out here as well. And that looks good to me. So I encourage you now to go ahead and try these problems here on the back. And you can check your solutions with what I have in uploaded to my Schoology account.